Hey guys, in this video we're going to continue our study of theorems. This next theorem is called the Binomial Theorem, and this one is a little bit different than the other ones we've talked about. You're not going to hear me mention the term roots or zeros in this video. This theorem is really about expanding binomials, and what I mean by that is taking a binomial and taking it to a certain power. Okay, so this theorem also has a little bit in the area of probability and statistics, a little bit of application there, but we're not really going to explore that today. We're going to look at how you use this theorem to expand binomials. So imagine I gave you the problem 3x minus 2, and I wanted you to take that to the fifth power. Okay, well, one way to do that, and the only way you know how to do that, is to take the binomial 3x minus 2 times itself 5 times, which is going to be a lot of foiling there and a lot of multiplication. Not necessarily difficult, but tedious. And then if I wanted to, I could even up it and say, okay, instead of 3x minus 2 to the fifth, do 3x minus 2 to the 12th. And then you would have to take 3x minus 2 times itself 12 times. And so that's just going to be a pain to do. Well, the binomial theorem allows us to do binomial expansion like this a little bit more quickly by using what is called Pascal's triangle. Now, you may have heard of Pascal's triangle before, maybe you haven't. It's basically a triangular array of numbers in a certain pattern that allows us to use the binomial theorem. And this is what Pascal's triangle looks like. So it starts at the very tip with just the number 1. Okay, and then the next row you have the number 1 and then the number 1 again. The next row is when it gets a little bit more interesting. Okay, you always start each row with a 1. The next number in the next row would be a 2. And then you end with a 1. In the next row you have a 1, a 3, and a 1. The next row you have 1, 4, 6, 4, and 1. The next row 1, 5, 10, 10, 5, and 1. Next row 1, 6, 15, 20, 15, 6, 1, 1, 7, 21, 35, 35, 21, 7, and 1, and then the last row 1, 8, 28, 56, 70, 56, 28, 8, and 1. And actually, I should not say that's the last row because Pascal's triangle actually goes on forever. So I could create the next row below that and the next row below that. But it's the last row you'll write on your notes here. So now you're probably asking yourself, okay, Mr. Yance, where in the world did you come up with this? Okay, well, if you'll look at this and analyze it for a second, which I want you to do, you're going to notice hopefully a pattern in the way the numbers are arranged. So I want you to take a second and look for any kind of patterns you notice on this. Go ahead and pause the video to do that, and then click play to check your answers, please. Okay, so some patterns you may have noticed. Obviously, the outsides of the triangle, okay, the perimeter of the triangle has all 1s, okay, so every row always starts with a 1 and ends with a 1, okay, so that is one pattern. That's not really the one I'm focused on here. Another pattern you may have noticed is if you go down the second diagonals, okay, starting right here, you go 1, 2, 3, 4, 5, 6, 7, 8. Also here, 1, 2, 3, 4, 5, 6, 7, 8. Okay, these diagonals here increase by 1. Okay, so maybe you notice that pattern right there. Again, that's not the one I'm looking at, but that is a pattern that does exist. The pattern I'm concerned with is once we get the 1, okay, in each row, once we get the 1, how do we get the next number? For instance, if I go down to this row right here, I start with a 1. How do I know the next number is 6? Okay, or even more interesting, how do I know the next number is 15? Well, if you look at the numbers above, okay, each number, so let's focus on this 15 right here. What are the numbers above it? The numbers above it are 5 and 10. Okay, 15 is between the 5 and the 10. Guess what 5 plus 10 is? 15. Let's go to this 21 down here. Okay, what are the numbers above the 21? 15 and 6. 15 plus 6 is 21. So to create each subsequent row after you start with the number 1, you take the two numbers above, okay, that number, add them together, and that's what gives you the next number. So if I wanted to create my next row down below, okay, I would start with a 1. 1 plus 8 is 9. 8 plus 8 is 36. 28 plus 56 is 84. 56 plus 70 is 126, and then we have another 70 plus 56, 126. And you'll notice that in every row you're symmetric. Okay, so you either hit the largest number once or twice. In this case, I'm doing 126 twice, and then it goes back down. We have 84 again, and then 36, and then 9, and then 1. Okay, so that's how you create Pascal's triangle. And before you ask, yes, Miriam, you have to know how to do this. Okay, that is how you create Pascal's triangle. We're going to use that in just a second in the examples below to expand some binomials. One other thing I want to talk about Pascal's triangle is how you number the rows. This first row up here, this one by itself, is actually called row 0. And then the next row is row 1, row 2, etc. Okay, so the second number in each row will tell you the row number. Okay, so this is row 2, this is row 3, row 4. Okay, but that first row, in order for that pattern to work, has to be row 0. Okay, so now we're going to use Pascal's triangle up here to apply what is called the binomial theorem. The binomial theorem says this, okay, for every positive integer n, if you take a binomial to that n power, you get this pattern here in terms of the binomial expansion. Okay, p sub 0, p sub 1, p sub 2. This probably makes no sense to you as you read this. If you notice below here, it says though p sub 0, p sub 1, p sub n are the numbers in the nth row of Pascal's triangle. So whatever, this is basically saying whatever power we're taking our binomials to, we're going to use that row in Pascal's triangle to allow us to expand the binomial. Okay, it's what essentially this theorem up here is saying. So if I go down to example 1 right here, I have the binomial a plus b to the 6th power. If I want to expand this binomial using the binomial theorem, I'm going to look at my exponent, which is a 6, and I'm going to start in the 6th row of Pascal's triangle. Okay, so I want you to go up and find the 6th row of Pascal's triangle. Remember what I told you about the rows. Okay, so the 6th row would be this row right here. Okay, so we're going to use that row there. And now we are going to expand this binomial using that row right there. So the first thing I start with is the first number in the row of Pascal's triangle I'm using, which guess what is always going to be a 1. So that's what I start with, a 1. The next thing I do is I take the first term in my binomial. Okay, the first term in my binomial is a. And I'm going to multiply 1 times a to the power that I'm taking the binomial to. That would be the 6th power. So 1 times a to the 6th power. Okay, then I take the next term in my binomial, which is b, and I take b to the 0 power. Okay, so it's going to be 1 times a to the 6th times b to the 0. That's going to create the first term in my expansion. Next, I'm going to add to start my next term in my expansion, and for the next term in my expansion, I start with the next row in Pascal's triangle, which is a 6. I'm in the 6th row, so next I start with a 6. I take the next term in my binomial, again, which is a, okay, the first term in my binomial, should I say, which is a, and now I'm going to decrease its power by 1. So over here it was a to the 6th, over here it's going to be a to the 5th. I then take the second term, b, and it's going to increase in power. So instead of 0 power, it's going to be b to the 1st power. So I have 6a to the 5th, b to the 1st. To get the third term of my binomial expansion, I go to the third number in Pascal's triangle, which is a 15 here. I do 15. A, the first term in my binomial, now we'll take it to the 4th power, so we'll decrease its power by 1, and then b, we will increase its power again. That makes it b to the 2nd power. Okay, and so this pattern is going to keep going on and on until we finish the terms in our binomial expansion. I'm on the 4th term now, so now I need to use the 4th number in my row, which is a 20. Now we're to the 20, so this will be 20. A to the 3rd power, b to the 3rd power, Okay, the next term, this will be my fifth term. Now I'm to the 15 again. So another 15, a to the second power, b to the fourth power, and then next we have 6, a to the first power, b to the fifth power, and then lastly we end with a 1 again. So we have 1, a is now to the 0 power, and b is now to the 6th power. Okay, so basically we're doing this pattern right here, if you haven't figured this out yet. We're taking the first number, or we're taking the number in Pascal's triangle, okay, going through the row, 1, 6, 15, 20, 15, 6, 1. That is the coefficient on each of our terms. Then we're taking the first number, or the first term in our binomial, which is an a, every time that number gets decreased by 1 in terms of the exponent, starting with 6 and going all the way down to 0. And then the second term b, we start its exponent at 0. It gets increased 1 each time until we get to 6. Okay, so my final answer for this problem, we're going to do some simplification here. Our first term is 1a to the 6th, b to the 0. That simplifies to just a to the 6th. So that will become a to the 6th. Our next term is 6a to the 5th, b. Then we have 15a to the 4th, b squared, plus 20a cubed b cubed, plus 15a squared b to the 4th, plus 6ab to the 5th, plus 1 times a to the 0 times b to the 6th would just be b to the 6th. So this is actually the polynomial you get if you multiplied a plus b times itself 6 times. This is the final answer you would get. We're going to, once we practice this enough, be able to do that a lot more quickly using this binomial theorem here. Okay, so let's go down to number 2 now and apply this again to x plus 3 to the 8th power. So this time you need to go to the 8th row in Pascal's triangle. So find the 8th row. And we are going to be using these numbers right here. Okay, this sequence of numbers right here. So I start out with the first number in that 8th row, which is a 1. And so my pattern tells me every single term I'm going to do the number times x to some power times, in this case, 3 to some power. So my first term is going to be 1 times x to my starting power, which is 8, times 3 to the 0 power. Next term, we go to the next number, which is 8 in Pascal's, so 8 times x to the 7th power times 3 to the 1st power. My next term, we go to the next number of Pascal's, which is in that row a 28, so 28 x to the 6th power, 3 to the 2nd power. Next term, we go to the next number in Pascal's, which is a 56, so we have 56 x to the 5th power, 3 to the 3rd power. Okay, next row, 56 we had in the last term, so now we have a 70, so 70 x to the 4th power, 3 to the 4th power. Next term, we go back down to 56, so now we have 56 x to the 3rd, 3 to the 5th. Next term, back down to the 28. So we have 28x squared, 3 to the 6th. And 2 more terms, we're almost there. Next term is going to go back down to the 8. So we have 8 x to the 1st, 3 to the 7th. And then finally that last term there, back down to the 1 from Pascal. So we have a 1 x to the 0 power 3 to the 8th power. Okay, you've never had this much more fun in a video before, I know. So now we're going to do some simplification here of the exponents. You have to be careful with your exponent rules here. So watch carefully how I'm going to simplify each of these. My first term, 1 times x to the 8th times 3 to the 0. 3 to the 0 is just 1, so that becomes just x to the 8th. Your next term is 8x to the 7th times 3 to the 1st. 3 to the 1st is 3. 3 times 8 is 24. So this will give me 24x to the 7th. Okay, so I need to do the exponent on the 3 each time and then multiply that times the coefficient before I go ahead and simplify here. So my next term here, 28x to the 6th, 3 squared. 3 squared is 9. 9 times 9, or excuse me, 9 times 28 is going to give me 252. So this will be 252x to the 6th. Okay, your next term, 3 cubed is 27. 27 times 56 is 1,512. So this will be 1,512 x to the 5th. The next term, 3 to the 4th. 3 to the 4th would give you 81. 81 times 70 will be 5,670. So 5670 x to the 4th. Okay, the next term, you're going to do 3 to the 5th, and then take that answer times 56. That will give you 13,608 x to the 3rd. Okay, so we've done the first 6 terms so far. Now we're to this term here, 3 to the 6th times 28. Okay, if you take 3 to the 6th and then take it times 28, you should get 20,412. So 20,412 x squared. This term here, 3 to the 7th, if you take 3 to the 7th and then take it times 8, you get 17,496, so 17496x. And then the last term, it's just 3 to the 8th times 1, so 3 to the 8th is going to be 6561, and x to the 0 means there's no variable on that one, so it's just 6,561. So you get this polynomial here, okay, this 8th degree polynomial with 9 terms. Alright, for the sake of time on this video and to not wear you out, we're going to do the other 2 examples in class. So I just wanted to give you a brief exposure to this binomial theorem. I promise it gets quicker the more you practice it. I know it seems daunting right now, but we'll go ahead and do those other 2 examples in class. So until I see you then, have a nice day. You are all wonderful people, and take care.